What specific problem does the Gemini embedding model aim to solve in the context of existing text embedding models?
The Gemini embedding model aims to address the limitations of existing text embedding models, which often struggle to generalize effectively across diverse tasks and domains. By leveraging the powerful Gemini large language model for initialization, Gemini embedding enhances the quality of training datasets through data curation techniques such as filtering low-quality examples and generating synthetic datasets. This approach allows for robust semantic representation learning through a contrastive learning objective, ultimately leading to superior performance on a wide array of embedding tasks. Additionally, Gemini embedding incorporates a two-stage training pipeline and employs hard negative mining to improve retrieval accuracy, thereby advancing the state-of-the-art in general-purpose embeddings across both high-resource and low-resource languages. Overall, it seeks to create a more adaptable and effective embedding model that excels in multilingual and cross-lingual contexts.
How does the proposed Gemini embedding method work? Please illustrate step by step, including the model architecture, training objective, and any unique components introduced.
The proposed Gemini embedding method operates through a structured approach that includes model architecture, training objectives, and unique components. First, the model architecture is initialized from the Gemini large language model, utilizing a transformer with bidirectional attention to process input sequences and generate token embeddings. A mean pooling strategy is applied to create a holistic representation of the input, followed by a linear projection to scale the embedding to the target dimension. Next, the training objective employs noise contrastive estimation (NCE) loss with in-batch negatives, where each training example consists of a query, a positive target, and optionally a hard negative target. The training process is divided into two stages: a pre-fine-tuning phase that adapts the model to encoding tasks using a large dataset of potentially noisy query-target pairs, and a fine-tuning phase that focuses on task-specific datasets with query-target hard-negative target triples. Unique components of the Gemini embedding method include the use of synthetic data generation for diverse training examples, data filtering to enhance dataset quality, and hard negative mining to improve retrieval performance. Additionally, the model soup technique is employed to average parameters from multiple fine-tuning runs, further enhancing the model's generalization capabilities across various tasks and languages.
Can you provide a simple yet illustrative example that walks through the key steps of the Gemini embedding algorithm, using a hypothetical input to clarify the process?
To illustrate the key steps of the Gemini embedding algorithm, let's consider a hypothetical input, a query, "What is the capital of France?" and a relevant passage, "The capital of France is Paris." 1. Pre-fine-tuning. Initially, the model is pre-fine-tuned on a large dataset of noisy query-target pairs, which helps adapt the parameters from autoregressive generation to encoding without using hard negatives. This step ensures the model can handle diverse queries effectively. 2. Fine-tuning. Next, the model undergoes fine-tuning on a mixture of task-specific datasets that include query-target hard-negative target triples. For our example, the model would learn to distinguish between the correct answer Paris and a hard negative like London, enhancing its retrieval capabilities. 3. Data curation. During training, Gemini is employed for data filtering and hard negative mining. It filters out low-quality examples and identifies hard negatives by scoring potential candidates, ensuring that the model learns from the most relevant and challenging examples. 4. Embedding generation. The input query and passage are processed through the Gemini embedding model, which uses a transformer architecture to produce token embeddings. A mean pooling strategy is applied to generate a single embedding that encapsulates the semantic information of the input. 5. Evaluation. Finally, the model's performance is assessed using benchmarks like MMTEB, where it retrieves the highest scoring passage, in this case, the capital of France is Paris, based on cosine similarity, demonstrating its effectiveness in cross-lingual retrieval tasks. This example encapsulates the essential steps of the Gemini embedding algorithm, showcasing its training process, data handling, and evaluation methods.
What are the theoretical and practical benefits of using Gemini embedding compared to traditional embedding models or previous state-of-the-art models?
Theoretical benefits of using Gemini embedding include its initialization from the powerful Gemini large language model, which allows it to leverage extensive pre-trained knowledge, enhancing its ability to generalize across diverse tasks and languages. Practically, Gemini embedding demonstrates superior performance on the massive multilingual text embedding benchmark, MMTEB, achieving state-of-the-art results with a border rank of number 1 and a mean score of 68.32, significantly outperforming previous models like multilingual E5 large instruct by +5.09. Additionally, it excels in both high-resource and low-resource languages, showcasing its robustness and adaptability. The model's training methodology, which includes a two-stage pipeline of pre-fine-tuning and fine-tuning with diverse datasets, further contributes to its effectiveness, allowing it to outperform traditional models that often overfit to specific benchmarks. Overall, Gemini Embedding's innovative use of synthetic data generation, data filtering, and hard negative mining enhances its training quality, leading to improved performance across a wide array of tasks.
How is the performance of the Gemini embedding model validated? What experimental design, datasets, and metrics were applied to demonstrate its effectiveness?
The performance of the Gemini embedding model is validated through extensive evaluations using the massive multilingual text embedding benchmark, MMTEB, which encompasses over 100 embedding evaluation tasks across more than 250 languages. The experimental design includes a comprehensive assessment across various task types, such as classification, clustering, and retrieval, ensuring a robust evaluation of its capabilities. Metrics used to demonstrate effectiveness include the border rank, task mean scores, and task type mean scores, with Gemini embedding achieving a first-place ranking on the public leaderboard and significant improvements over previous models, such as A+5.09 increase in the mean score. Additionally, the model's performance is rigorously tested on cross-lingual benchmarks like XOR Retrieve and ExtremeUp, showcasing its strong retrieval capabilities across multiple languages. The ablation study further elucidates the factors contributing to its superior performance, reinforcing the model's effectiveness across diverse tasks and languages.
What are the identified limitations of the Gemini embedding approach, and what suggestions for future work do the authors propose to address these limitations?
The identified limitations of the Gemini embedding approach include potential overfitting due to excessive hard negatives, which can degrade performance on retrieval tasks. The authors suggest exploring regularization techniques and improved hard negative sampling strategies to mitigate this issue. Additionally, they recognize the need to extend the embedding capabilities beyond text to include other modalities such as image, video, and audio. To address these limitations, the authors propose curating multimodal data tasks that are suitable for learning generalizable representations and developing training recipes that balance performance across different unimodal and multimodal capabilities. This comprehensive approach aims to enhance the versatility and effectiveness of the Gemini embedding model.